So the idea is that I'm going to take about 20 minutes or so. I'll run through just some metrics. So you've seen some different ways you can quantify resilience, right? Because we've talked about it in very qualitative terms. So we'll quantify it a little bit, and then we'll wrap up with a little exercise that we'll do per table. We'll calculate the loss probabilities of different components of a power system. And it's an illustration of a mathematical framework called performance-based earthquake engineering. And so I think it'd be interesting. It's a skill that we can all learn in like an hour, and hopefully would be useful to you in your studies or in your own analysis or just for fun or whatever. So that's the plan anyway. That's what we'll close with. So let me start with talking about 20 minutes or so about some metrics. Right? So some of these you'll have seen before. Some of them I'll move super quickly through. Some of the ones that power systems people see quite a lot is loss of load probability. So there you're doing a study where you determine the probability that you will not be able to serve the load, that you don't have enough generation to serve the load. Loss of load expectation is a similar one, but instead of the probability that you won't be able to serve the load, it's the number of hours or days a year that you're not able to serve the load. Effective load carrying capability, also known as capacity credit. So that's sort of the security equivalence of usually applied to variable sources like wind or solar. Right? Like if you put a 100 megawatt wind farm on your system, that's good, but it may or may not be there. Right? Or it may be there somewhere between 0 and 100 megawatts. And so it certainly does add to the supply of your system. It's better than 0, but it's also not 100 megawatts. It's somewhere in between. Right? And when you do a study of sort of the security that adds to your system, what you end up with is a number we call capacity credit. So we might say a wind farm has a 20% capacity credit. Right? So it adds to the same security of supply of your system as a system that was 20% of that nameplate capacity. Right? So that's one metric. Another one is capacity margin, which is just simply the normalized capacity over your peak load. So how much headroom you have normalized to your load. Right? So these are some basic metrics, certainly that power systems people are familiar with or use. Some other power system ones, SAFE, SAIDI, and CAIDI. SAFE is the system average interruption frequency index. So the total number of customers interrupted divided by the total number of customers. So what fraction of your customer base had a load interruption? SAIDI is very similar. It's the total customer interruption durations divided by the total customers. So the average interruption that a customer will see, is that measured in some hours per year or something like that. And then last is CAIDI, which is the total customer interruption duration divided by the total number of customers interrupted. So for customers that were interrupted, what's the length of time, those average interruption lengths? So again, 3 very simple, very easy to use metrics, generally used by the power systems community, particularly planners and things like that. But let's talk a little bit. So that's on the power system side. We're not really focusing on the power system side. So how can we look at resilience in general? What kind of metrics are there for resilience? So I'll show you 2 main ones. I'll show you this one, and then the one that we'll do here is this exercise. First one is, let's say that we have defined some function of the system. So that's R. So this is system is more good, more better, has more function, does what it's supposed to do like it's supposed to do. Okay? And then this is time. So here my system is cooking along, doing what it's supposed to do, and now something bad happens, and I lose function of the system. I'm in a degraded state for a while, and then I recover. Right? So one metric that we might use are the different corner points of a plot like this. Right? So you might say, well, I want to design my system so that this recovery time here is a certain length of time, is a certain number of hours or a certain number of days. Right? Or you might want to define this right here, the difference between your pre-disturbed function and your post-restored state, before you go into long-term fixes, but sort of what you're able to get back up to in the short term. Right? That might be another metric that you might use. Right? So a plot like this, right, defining those corner points, might be metrics that you might use to define certain performance of your system. But we can go a little further with something like this. Okay? This is the same thing, it's just simpler. Actually, let me just skip this one. I'll just show it here. Let's go. I can illustrate it with an example that works better. So we saw this one, right? This was our Tohoku number of homes without power. So we were down here somewhere, probably not 0, but close to 0, right? The earthquake hit, and we got a bunch of homes without power, right? And then we start rebuilding the system, and we've recovered. And now we don't have many homes without power. And then there was another earthquake that happened, right? But then we recovered. So I want to make that look like that. But the way it's defined right now, they're complements of each other. Because this here is more good, is more goodness of the system. But this here was homes without power. That was more bad as I go up. Right? So I got to flip this. Right? I have complements. So I'm going to flip that one over, and that's what I get here. And so now you see this starts to look like that resilience curve that I showed before. This is how functional my system is. Here something bad happened and I lost a bunch of function of my system, but then here I recovered some function of my system, but not quite all the way yet. And I left out the second earthquake here. This is just the first earthquake. So does that make sense what I have there? Is that good? Just a complement of that. Okay. So how can I use this to talk about resilience? One thing I can do is I can say I have a target resilience, and that's the black line. So blue is what happened, blue circles, and black is maybe what is the best case scenario, right? Unrealistically best case scenario, where I just sailed right through it like nothing ever happened, right? I had total function before the earthquake happened, and I have total function after. That's like totally unrealistic desire, but let's use that. Let's use that anyway, as that's the best I possibly could have done. So what I can do to define a numeric metric is I can take the ratio of the area under these curves. So, for example, for my target resilience, that's the black, right? I'll take the area under this whole box, right? This number of homes with power times this many days, right? That's the area under that box, right? If we remember back to our calculus, right? So I have home days. And that's what's shown right here. That's the second one. The sub t means my target, right? And if I integrate what's shown right here, if I integrate that box, I get 287 million home days is the area under the black, right? Then I can divide that by the area under the blue, right? So the area under the blue is the area of this rectangle, and then the area under here. So I'll integrate that, okay? And that's the top one. That's what I actually got. And that's 266 million home days. So the ratio of those then is a firm number that defines the resilience of that system, 0.92, right? If I perfectly met my target, if my blue response perfectly met my target, what would my resilience be? It'd be 1, right? The area under the black would be the area under the blue, okay? So 1 is the best I could possibly do. Here I did 0.92 defined this way, okay? Which seems quite excellent. Yes?
But if you had started at 0 instead of -5, it would be significant.
So that would be your call about where you want to pick that at the beginning. So I allowed for a little bit of a buffer on the front end there. But yeah, certainly if you cut it off there, then that number would drop a little lower. Yep. Yes?
This is great from an engineering analysis standpoint. An interesting next step would be, from a policy perspective, looking at the cost of that loss of power to medically fragile people, et cetera, and that's what Bonneville Power and others need to be able to justify the capitalization to get the benefit that offsets the cost. And so I've heard from utility people, the grid goes down, people die. Yeah. It is one of the phrases I've heard, and that's probably pretty accurate. So, and people like Dr. Bluffstone here at Portland State that does cost-benefit analysis, I have a feeling there are some ways from people who know how to do that well to start putting a qualitative measure into how much that's going to cost.
Yeah. Yeah, absolutely. Yeah, I totally agree. You could absolutely extend it that way. Yeah. But as a basic metric, does that make sense? So a basic idea if you have a system? Yes.
This doesn't reflect when the incident's going to happen, because if you look at 15 days, it's important when it's happening, the impact, when it's like a first day or day 14 that this is happening. So if 14 days without no accident, everything is good, then toward the end going to happen. But this doesn't reflect when it's going to happen.
Why did I choose -5 and 15?
You're showing the initial condition, and then before that.
Yeah, why -5 and 15 though? Why not -4 and 14? Because I felt like it. It was my choice. It was my choice, right? I mean, so if I was going to use this metric, I would just be consistent in how I used it, right? But there's no, as far as how far before, how far after you want to account for is totally your call in how you set up the metric. Yeah. But as long as you were consistent in the way that you used it, all your numbers would be consistent relative to your own analysis. Right?
The one thing is here is that the event happens, and the one thing that we don't know is it could happen 199 years from today. So that's, for me, the hard thing to argue about getting management on board is like, well, it hasn't happened yet, type of thing, you know?
Yeah.
But it's going to, you know?
Now we've talked about it.
You control that rise time. It seems like your gain would be a function of how much money or resources you have to dump into that restoration.
Yeah.
And how well prepared you are.
Yeah, because the steeper this line, the more money that you'll have to put into it, right? Yep. And also the closer that line gets. So, yeah.
It's just a PID, you know?
Yeah. I mean, it's a simple control system will take care of it. Take that error right out. Yeah. Make sense? Okay. Talk about a couple other metrics. So that was one metric. Talk about a couple other, particularly this will be relevant for the exercise that we do. Vulnerability functions. This is another really cool report. Again, I'll put this up in the repository, so you'll find this afterward. This is from this ATC 25, also known as FEMA 224 document. It's a little old, 1991, but it was a really comprehensive effort to go through and to say, well, dams are made of this much concrete and this much steel, and substations are made of this type of material. It's really crude, but it was nonetheless an attempt to try and say, well, these types of structures are made of these certain things, and we know that when we shake these certain materials this certain way, they tend to fail in this certain way. So it was an idea to try and work backward and try and figure out sort of really how resilient different types of structures were. And they go through a lot of structures, but they go through a lot of specifically electrical structures. So they talk about transmission towers, and they talk about substations and things like that. So I think there's a very wide error bars on their estimates, but nonetheless it was a methodical way to try and figure that out. One thing that they show is a vulnerability function. What you have here is a vulnerability function is something where you have like a shaking input. So I'm going to talk about it in the context of earthquakes, so it's shaking, but could be wind speed if you're talking about hurricanes or things like that, right? But anyway, I have a shaking index on an input and then a % damage to the system. And they have 3 different curves here that were determined 3 different ways. But anyway, this is an example of a vulnerability function where you say, well, if it shook really bad, a magnitude 9 on a modified Mercalli intensity scale, right, you have almost 75% damage, right? If it's 10, you have almost 100% damage. Right? And so you're saying there's a certain % damage to your system as a function of your input. Right? That's another type of metric that we can use, and it's something called a vulnerability function. This particular one is an exponential function shown here. So the amount of damage, right, as a function of the MMI is an exponential function. Another example of a vulnerability function, and again, I'll put this paper up in the repository, really, really good paper. There's been a couple mentions in the Nisqually event. This is a really good paper where what they did is they took a look at the distribution system around Seattle. And what they did is they took the shaking, the peak ground accelerations that we're seeing, and that made a contour map around Seattle. And then what they did is they took a look at the percentage of distribution system that was damaged within a contour line. So then you had a certain fraction of distribution damage as a function of the PGAs, the amount of shaking. And what you get then is you get a curve like this. And then they fit this model to it. They fit a sigmoidal or a logistic function to it. So just another example of what we call a vulnerability function. So it was a % damage of a certain system as a function of the shaking input. And there's 2 that are shown here. This one is for Nisqually, and then they compared it to Kobe. There's one in Kobe. So it's kind of interesting that they compared this together. There was a discussion earlier in the day that I wanted to remember when I got to this slide. And that is, there's also an interesting discussion in this paper. There's 2 parameters. So a logistic function looks like this. There's 2 parameters. There's a beta naught and a beta 1. And that affects the left-rightness of this curve. And one of the other parameters affects the steepness of the curve. So it's 2 parameters that you have to fit. Is its left-rightness, but also its steepness. And in that paper, they have an interesting discussion about the brittleness or ductility of systems. So in other words, if you have a really steep line, that means that as you go from here to here to here, you won't have much damage because the bottom part of the sigmoid will lay really flat, but then it will suddenly shoot up and then lay flat up here. So a steep line means that you don't have damage, you don't have damage, you don't have damage, whoa, you have a lot of damage. And it happens really fast. And they refer to that as a brittle system. And they were sort of raising as a point of discussion for system designers. It's like, if you harden a system, if we make a system really, really hardened against some external input, are you risking making it brittle? So that you can take a hit, you can take a hit, you can take a hit, but then when it fails, right? And it fails badly. And that just wasn't interesting. It kind of came up earlier in the discussion. And there's a discussion of that in this paper. So again, I'll put this in the repository, so please take a look at that. But anyway, just another example of a vulnerability function, where you have some input and you get a % damage to the system. Okay? And also as an opportunity to show it modeled in a different way as a logistic function, which I think this is actually much more, personally as a modeler, I do a lot of modeling, I think this model is much more sound than doing an exponential model like that. But just an example of two different ways of doing it. So now I want to talk about something else called a fragility function. And that's going to be most relevant to what we're going to work on here shortly. A fragility function is a little different than a vulnerability function. A fragility function is the probability that you're in a certain state. And this was from a paper, again, I'll put this in a repository. This was from a paper on a finite element analysis of a 420 kilovolt circuit breaker. So they didn't actually test it, but they did it with FEA. And what they did then is they determined the probability that it was moderately damaged or severely damaged. And so what defines that probability is something that's called a fragility function. And so for example, if you have, for this particular device that they looked at, so they have this very strange convention of using the slash here for a decimal. Have you ever seen that before? I thought, is that a mechanical engineering thing? I've never seen that. But in this paper, they did it. I don't know. And I asked some other mechanicals, like, oh, that must be your deal. I'm like, I don't know, never seen it. So anyway, so if you have 0.2 PGA, you have about a 25% chance of being severely damaged. If you have a 0.2 PGA, you have almost 100% probability of being moderately damaged. So do you see what that's showing? It's showing a % probability. It's showing a probability that you're in a certain state. Yeah, that's what a fragility function strictly does. And that's what I want to make sure that we get that right, because we'll work with that shortly, with fragility functions. So what would a fragility function look like for something that's more resilient? So if I have this fragility function, if I can push it that way, I will make it more resilient. Right? So as an illustration, let's say that I have this amount of input, this amount of shaking. Right? Before I enhanced my system, the black line, I had 100% chance of failure, or I had 100% chance of being in that, whatever damage state that described. But if I'm more resilient, right, then this has a 20% chance of being in that damage state. So resilience curve being pushed that way is a more resilient system. So just to say that again, so the vulnerability functions, there's an estimate of the reduction of functionality. In other words, the % damage, right? So it's what % damaged I am as a function of my input. But a fragility function is the probability that I'm in a certain state of damage given an input, right? So it's a probabilistic measure. Does that make sense? That's just some of the metrics that I had. But otherwise, we'll do this exercise. Any questions on that? Okay, let's do this exercise. So what I'm going to do is I'm going to guide you through the first part of it, and then we'll work on it together after that. And a couple people in the room know how to do this, and so we'll go around and help people out. So you should follow along with the slides that you have. Okay, so we're starting on the slide 144. So there's a couple slides of introduction here, and then we'll go through a worked example. Okay? So this PBEE stands for Performance-Based Earthquake Engineering. This came out of efforts of the Pacific Earthquake Engineering Center and Resource Center in California. It's been revised a little bit over the years, but this is, I think, the best current description of it. So the idea is that you have a particular asset. So again, your asset could be, we have different people that are representing different systems in this room, right? But sticking with the power systems, right, this might be like a circuit breaker. So first thing we do is we say we have a model that model. So what this notation means, you'll notice the P and then the H and then the bar and then the A. What that means is the probability of some hazard, that's H, and what the vertical bar means given, or using the information of. So given that asset. So I have some probability of some hazard for that asset. So from there I can determine that there's a certain probability of a certain hazard. From there I move on to say, well, if that hazard, given that hazard, there's a probability of a certain response of the system, right? If there's an earthquake, there's some probability that the system responds in some way to the earthquake. So now I have a probability of response. Once I have a probability of response, I can determine the probability that I'm in a certain state of damage, given that response, right? So now I have some probability of damage states. When I have a probability of damage, from there I can determine a probability of loss, given that damage. Right? So that system is a certain amount of damage. What's the probability that it's in a certain loss state? Right? So what would be loss states? Loss states might be something like loss state 0 might be that it's not that it works totally fine. Right? One loss state might be that it's completely gone. Another loss state is that it's lost half of its load or something like that. Okay? Again, as the designer of this methodology, you have to determine what those states are. Right? But and we'll go through some examples of that. Okay? So then the question becomes, what I really want to get to is I really want to get to here. Right? This is really the end question I'm trying to get to is, what's the probability that I'm going to lose that circuit breaker? That's really the question, right? How do I get to here? Well, I started here, and there's a whole bunch of intermediate steps, and I get to here. But how do I jump to this end? And what I need is to solve this, which we call the triple integral. Okay? Basically, what I need to do is I need to integrate every probability. I need to integrate every single possibility that could happen and add a weighted sum of all those up to get an ultimate last probability of loss. So strictly speaking, strictly mathematically speaking, you get a triple integral like this. Okay? So we can totally solve this if we remember our calc. We can totally solve it, and we have these functions. Right? But what I'm going to show you is a simplified version of it in a discrete form, in which this integration simply becomes the multiplication of matrices. Okay? Here's what it'll look like in a discrete form. Just an example, something like this. I have some asset. What should this asset be? Just pick something. What? Substation. So I have some substation, right? And I'm going to pick two hazards. I'm going to reserve the 0 state for meaning nothing bad. So hazard 0 is, what do you guys call it? Blue sky day? Yeah, blue sky day. Right? Hazard 0 is everything's totally fine. Hazard 1, let's pick something. We'll just say that's a Cascadia Subduction Zone 9. Okay, that's a 9.0. We'll pick that. But again, you can apply this methodology. We're talking about it in the context of earthquakes, but this could be for anything. If you run an industrial plant, this could describe any given threats or hazards that you might fit. It doesn't have to be specific to earthquakes, but we're going to do with that example. Okay, so this is going to be we're just fine, and this is going to be a Cascadia, a bad magnitude 9 earthquake. So what you'll notice then in the branch in between is the probability. So if I start here, this is the probability that I go here, and this is the probability that I go here. Does that make sense? This structure right here is something called a Bayesian network. And it's people that spend their whole academic careers or professional careers doing Bayesian statistics. So I start here, so there's some probability that I go here, and there's some probability that I go here. Okay. What do you think about what special property do these two probabilities have? They have to sum to 1. Exactly right. Right? I have to go to one or the other. Okay. It's either a blue sky day or it's not. What's that?
There's a whole range of possibilities in between.
This diagram. The simplified diagram, there's only 2 possibilities.
And this one you're limited to 2. Yeah. It's either a Cascadia Subduction Zone 9 or not. Right? So you're exactly right though. For simplicity's sake, I'm saying that a Cascadia 8.8 is a blue sky day. Right? So exactly right. So if you're doing to really do this full analysis, you would put as many hazard levels in here as you wanted to account for, right? Which could obviously get complicated, but if you're programming this, who cares? You can have these matrices be hundreds by hundreds, right? But for the sake of illustration, I just kept it to 2 hazards. One is everything's fine, and the other is something bad happened, right? So those probabilities add to 1. Right? So say we went to everything's fine, right? From everything's fine, there's some probability that I go to response state 0. So remember, response state is the excitation of my system. So in our substation, so in this case, our responses for the substation are going to be the PGAs of the substation. So how much shaking the substation has, right? So response state 0, again, sticking with my theme where 0 means nothing. Okay? This is going to be there was no shaking of the substation. This is going to be moderate shaking, and this is going to be severe shaking. Does this make sense? Okay? And again, what special properties do these 3 have?
Yeah, the likelihood is 0.
Yeah, they have to sum to 1. Right? They have to sum to 1. Right? I either have to get that response or that response or that response.
Assume that happens. One of those 3.
Well, okay, when you multiply this, you get it. Oh, okay, okay.
So far, so good? So the sum of any leaving any of these nodes will sum to 1, right? Because I have to go to one of those things. Does that make sense? Okay. I've been teaching for a long time. I know when things are like teetering. I can say you're not giving me a good feeling right now. So then what you have to do is you have to ask questions if you don't know, because then it's on you. Okay? But we'll keep going. All right? So our response state 0 is nothing. There's no shaking, moderate shaking, heavy shaking.
How can you have a blue sky day with severe shaking?
Excellent question. So these numbers right here, right? These are probabilities. This is a probability that I go here, probability that I go here, probability that I go here. If I'm in a blue sky day, what do you think the probability is that I go to no shaking?
1.
It's 1. So what will be the probability of this and this? 0. Excellent. Excellent. Does that make sense? Okay.
So are you okay, so the hazard is a Cascadia 9 event. Is that how you're defining it, or are you defining a hazard as a PGA of a certain amount given that substation location in relation to the?
No, I'm saying that it's just, no, I'm saying this, I think the first part, yes.
Okay, so then locate proximity to the fault, occurrence period, soil conditions are all factored in, right, into response statements?
And hopefully that'll make a little more sense when we go through the example. Okay. Does that make sense so far? You kind of see how this is going to work? So once I go to a certain response state, so let's say response state 0, which is no shaking, then I can go to 2 different damage states. So let's say for this damage, for this substation, let's say I define damage state 0 is it's fine. It works fine. Let's say damage state 1 is total destruction. Okay? I'm just going to say those two. It's either all upright and beautiful, or it's like a picture Leon showed in China where it's all on the ground. So if I have no shaking, what do you think the probability is that I go to beautiful substation? 1, right? And I'll have roughly 0 chance that I go to total destruction. Does that make sense? And then again, so then these two allow some flexibility. You could kind of stop right here. It'd be kind of intuitive to just leave out the loss state, and you arguably could. But the loss state allows you an additional degree of flexibility where you then can link like a specific description of damage to some specific description of the actual functionality of the system. Because you can have something that's damaged but can still work. Right? In our case, though, if I define loss state as, let's say loss state 0 is that I haven't lost anything. The substation has full capacity. And loss state 1 is I've lost all capacity. Right? It's completely gone. So if that was the case, then I just have 1 would go here to here, 0 would go here to here, 0 would go here to here, and 1 would go here to here. Right? So that damage to loss step, there's a degree of freedom in how you set that up. Okay? And hopefully it'll make a little more sense when we go through this example. But does that kind of make sense as to what you're looking at there? You're looking at a bunch of different states and the probabilities that you can move between those states. However, when we set this up, what that allows us to do is, remember, we can do actually some simple linear algebra to account for all of these probabilities. Because really, here's the question. What's the probability that my substation is completely lost? I have to account for this path. I have to account for this path. I have to account for this path. Right? There's many different paths through the network that get to L1. Right? There's many different ones. I have to account for all of those. And that's what we're going to show the method how that works. It just ends up being multiplying matrices. That's all you have to do. Does it make sense so far? Okay. Here what this is just these matrices. So here I'll show you this. So remember these two, the probability that I have hazard 0 or hazard 1, okay? That's going to be this matrix right here. Probability of hazard given an asset. This one right here is this number. And this one right here is this number. Okay? That's that first matrix. That first matrix just holds all the probabilities that I go from asset to hazard, the first layer of that. This matrix holds all the values that take me from this layer to this layer. Okay? So I'm at hazard 0, probability that I go to response 0 from hazard 0. That's right here. Next one, probability that I go to response 1 from hazard 0, right here. Okay? And this one here is this one. Right? So you see this top row of this matrix is these 3. Bottom row of this matrix is these 3. It's pretty gutsy to be doing this math like at this time of the day. It's good though, right? Just bear with me. You can do it. We can do it. Okay? Does that make sense? So what property do the rows of those matrices have? They sum to 1, right? This plus this plus this equals 1. That's this and this and this. So the sum across this row is 1. This, and this are these 3 probabilities, right? So they sum to 1. This matrix is this layer, right? This probability and that probability, that's top row. This probability and that probability, right? Both of them that leave R1, this row, right? And this is the other one. Again, those sum to 1. Make sense so far? So here's the thing. What is the probability that I go from here to these? What if I skip the middle? What I need to do is I need to multiply these 2 matrices together. That will take me from here to here. Oops, went back on. Right, and that's what's shown right here in these multiplications. So ultimately, to get here, this was really the final question. What's the probability of loss given the asset? What's the probability of there from here? Multiply those matrices together. Right? That's the integration of all of the probabilities. It's the integration and summation of every possible path through the network. Yes?
Can you go back to the network?
Yeah.
Why isn't there a D0, D1, D2 of okay, damaged, total loss?
Yeah, you can totally do that. Yeah, so it's very arbitrary what I set up. Well, it's not arbitrary. I picked something that was very simple. Right? But if you wanted a very complete description, you could add many more damage state definitions. And in fact, we'll see, I think in my other example that we have 2, I think the other example is 2, yeah, has more damage states. Yep. So far, so good? Okay, let's do an example. Let's take this power system. This is a simple 4-bus system. This is from an old textbook from Granger and Stevenson. I just made this up. This isn't real. This is just a toy. Right? This is a simple 4-bus system. But I said, let's call this the coast and let's call this the valley. So this stuff is going to get shaken badly, and this stuff isn't. Right? So these are buses in a power system, but we'll say they're substations. Okay, so I have a substation here, I have a substation here. 4 substations. That's a generator. That's a generator. What are these arrows? Loads. Okay. And what are these lines? They're lines, yeah. We'll call them branches. In the terms of power systems analysis, we'll call them branches. But they're transmission lines or distribution lines, whatever you want to think of. Okay? They're copper and aluminum that stretch across here that allow electrons to flow. So I have 4 kinds of assets. I have generators, I have loads, I have branches, and I have substations. I have 4 types of assets on this system. Some of the assets are on the coast, and some of the assets are on the valley. And 2 of the assets actually stretch across. I'm not going to deal with that here, but you'd have to define some other category for something that goes across. Does this make sense so far, what we're talking about? Oh man, what if we got an earthquake? Let's take a look at this valley load. Could be Portland, could be Corvallis, could be Albany, Salem, Eugene. Right? So let's take a look at this valley load. We're going to calculate the probability that we're going to lose this valley load. We're going to use this network. A little more complicated than the one before, but the idea is exactly the same. I have this asset, that's going to be my valley load. I have this asset. I'm going to define 3 hazard states. Hazard state 0 is everything's fine. Hazard state 1 is going to be an 8.0 Cascadia, and hazard state 10 is going to be a 9.0 Cascadia. Now you may wonder, why does it go 1 to 10? Don't worry about that for now. I'll come back to it in a little bit. Okay? Just consider I just left out the other ones. You can think of it that way. That's essentially actually what I did. But you can just think of it as it's just 3 for now. Hazard state 0, hazard state 1, hazard state 10. We're going to define 3 levels of response. I'm going to talk about this in the next slide. 3 levels of damage and 3 levels of loss. So what are those? Hazard state 0, no earthquake. Hazard state 1, Cascadia 8. Hazard state 10, Cascadia 9. My response states. Response state 0 is no PGA. Okay, nothing, there's no excitation of that system at all. Response state 1 is 0.05 to 0.1. Response state 2 is 0.1 to 0.2. And response state 3 is 0.2 to 0.3. Okay, so 4 levels of PGA excitation, 1 0 state and 3 others. Damage states, I said okay, partial damage, not okay. Okay? 0 is fine, 1 is partially damaged, and 2 is completely damaged. And I'll admit to that being pretty crude. It's actually recommended in this methodology that you try and be really specific about those damage states. So it'll be something like, in this case, we're talking about an aggregate load, so it's hard to be very specific about it. But if we were doing a generator instead or something like that, then like damage state 1 might be loss of auxiliary system. Damage state 2 might be off of the foundation. Damage state 3 might be the shaft is cracked or broken or something like that, right? It's where there's specific definitions. However, for our purposes, I've kept it really general. So okay, partial damage, not okay. And then so our loss states then is that load, it's either, so if it's not lost, it's just drawing full load. If it's in loss state 1, it's drawing half of its load, so it's partially been damaged or partially destroyed. And loss state 2 then is it's drawing 0 load. It is completely gone. Does it make sense? Okay, let's work with this then. So I'm going to give you these first 3 numbers. I'm just going to give these to you. I'm not going to derive them. And they're actually, to be honest, I just pulled them out of very crude approximations. Let me stress this to you. None of the numbers I'm going to use in this analysis are necessarily true. The goal is to illustrate the methodology. Okay? It's not that the numbers are exactly right. Okay? That's a problem for another time. But I have three numbers here. So you'll notice, you can see it. I have 0.985, 0.010, and 0.005. So what does that mean? So for this valley load, what's the probability that I have a blue sky day? It's 98.5% probability. What's the probability that I have a Cascadia 8 earthquake? 1% probability, right? And a 0.5% probability that I have a Cascadia 9. Okay? Again, those numbers are not strictly determined in any way. Okay, just made them up, very approximately. Does that make sense? Okay. We're just going to start with that assumption.
But if you did this on the 50-year time, I'm sorry.
It's kind of in that ballpark, yeah. It's kind of roughly, it's roughly based off of that, yeah. Yeah, but then rounded to make them kind of nicer, and yeah. So this next part. So the next part is then I got to get these next ones. So let's solve this next layer to go from hazard to response. So you'll notice from hazard state 0, I have to go to 4 different responses. So it's a probability that I don't shake at all, that I have light shaking, that I have moderate shaking, or I have severe shaking. For a Cascadia 8, there's some probability that I have no shaking, light shaking, moderate shaking, and heavy shaking. So how do I determine those? Well, now I need those fragility functions to help me with this. That's what's shown on this slide. This is my valley region response. So remember, we're talking about the valley because this was a valley load. When we do the coast example, I have a different set of curves for the coast. So my hazard states, again, so what I'm trying to get is I'm trying to get these numbers from between this layer and this layer. So I need these 12 numbers to go from hazard to response. So my hazard states are 0, 1, and 10. See that here? 0 is not shown, but I have 1 and 10. And the response states that I have are 0, 1, 2, 3, and 4. Right? 0, 1, 2, 3, 4. Is that good so far? Make sense? So I think that hopefully that makes sense. Here's the only next tricky part of this whole analysis, is how to read that fragility curve. Once we get this, you'll get all of the rest of it. It will fall like dominoes. Okay, so here's the next part. I'm just going to give you, we're going to solve this one right here. We're not even going to consult the fragility curve. We're just going to give it to you. So if it's a blue sky day, what's the probability that I'm not shaking? 1. Well, what's 1? So we're just going to put a 1 there. That's going to be 1. So what are these 3 numbers going to be? They're all going to be zeros. 1, 0, 0, 0. We're just going to give that one. That's just a gimme. Does it make sense? Okay, but how about this next layer? From hazard 1 to these responses. What does that mean? Remember that what these 3 curves define is the probability of being in a certain state. So let's think about this. The blue one is the probability that I'm in response state 1 or greater. 1 or greater. And you'll notice that's 0.5, right? We're going to start with hazard state 1. So we're doing these 4 right here. Everything that's leaving hazard state 1. Okay? So blue, you see that's at 0.5. That means there's a 50% chance that I'm in response state 1 or greater. So it also could be 2 or it could be 3. Right? It's a 50% chance that I'm in 1, 2, or 3. So what's the probability that I'm in 0? I'm in response state 0. 0.5. Right? There's a 50% chance that I'm in 1, 2, or 3. So therefore, there's a 50% chance that I'm in 0. Does that make sense? So you'll notice it's 50% between here and here. That's the probability. So that's this number. That's the probability that I go from hazard 1 to response state 0. We'll do a couple examples. Okay. We'll look at the next one, the orange curve here. The probability that I'm in response state 2 or greater. The probability that I'm in response 2 or 3. What's the probability that I'm in response state 2 or 3? 0. There's no chance that I'm in 2 or 3. What's the probability that I'm in response state 3? Also 0. So there's no chance that I'm in 2 or 3. So if there was a 50% chance that I'm in 0 and no chance that I'm in 2 or 3, what's the probability that I'm in 1? 50%, the other 50%. Okay? It's this distance. It's this distance right here. So that'll become even more clear on this next one. So reading these actually becomes really easy in the next example. So these numbers then, I'll show you it's going to be 0.5 and 0.5. I went to the next slide over. 0.5, 0.5, 0, 0. Okay? Here's this. So hopefully this example is even more illustrative. So now what if I'm in hazard state 10? What's the probability that I go to response state 0, 1, 2, or 3? So from here. Okay, now I got to look at hazard state 10. What's the probability that I'm in response state 1 or greater? 100%. 100% chance that I'm in 1 or greater. Right? So what's the probability that I'm in response state 0? No chance. So in other words, just to not lose track of what we're talking about, that means if there's a Cascadia Subduction Zone earthquake, magnitude 9, for that valley load, what's the chance that it doesn't shake at all? 0 chance. No chance it doesn't shake. Does that make sense? Okay. What's the probability that I'm in response state 1? I know it's a 100% chance that I'm in 1 or greater, but what's the chance that I'm in 1 and only 1? It's this distance. It's this distance because the orange line is the probability that I'm in 2 or greater. Right? So the difference between being in 2 or greater or 1 and greater is the probability of being in 1. Right? So this little distance right here. So it's about a 3% chance that I'm in response state 1. What's the meaning of this distance here? The probability that I'm in response state 2. Okay? And the meaning of this distance here? The probability I'm in response state 3. Right? So the trick to read these, right, you can work it all backwards logically like I talked about, but if you want just the mnemonic shortcut, it's just to look at these distances between here, and those are those probabilities. Here's the probability that I'm in 1. Here's the probability that I'm in 2. Here's the probability that I'm in 3. Okay? So it's about a 3% chance that I'm in 1. It's about a, 39-ish that I'm in 2. And then about a 58 that I'm in 3. Wow, you guys read that really well off of this. Okay? So that's what's here. Does that make sense? Okay, don't worry. Well, you'll get a chance to work on it. So I think that's all you have to do going forward. So for the next layer, I need the fragility functions that tell me the probability of being in a certain amount of damage. So that's what this one is. So you notice that this one has response state as an input and a probability of being in certain damage states, right? Because I've got to go from response to damage. That's our next step. So I'm in a certain response state, and here's the probability that I get that this is probability that I'm greater than damage state 1, and probability that I'm in greater than damage state 2. So just like, for example, let's look at these 3 down here, right? Probability that I go to damage. So if I'm in response state 3, I'm right here. Right? There's a 100% chance that I'm 1 or greater, so there's no chance that I'm going to damage state 0. In other words, if I experience the most shaking, there's no chance that I'm not damaged. Okay? This one is going to be 0. Okay? There's a 100% chance that I'm in 1 or greater, 0% chance I'm 0. Okay? So this distance then is the chance that I'm in 1, which is 0.5, and this distance here is the chance that I'm in 2, which is 0.5. Okay? So again, going, or very close to 0.02, 0.48, and 0.5. I guess I left just a tiny sliver on that one at the upper end, but 2%. Yeah. Does that make sense? Kind of. You have to do it to make it make sense. That's what the rest of it looks like. Actually, the last one is really simple because to go from damage to loss is just maps straight over. Because I just said if it's fully damaged, it's fully lost. If it's not damaged, it's not lost. So that maps over really simply. Okay? So then you get a network that looks like this. So once I have this complete network, now I can calculate these probabilities by multiplying the matrices of all those intermediate values. So here, for example, this is the matrix of the values that go from asset to hazard. That's these three, right? That's this one, this one, and this one. Again, the row has to sum to 1. Okay? Next matrix, this is just repeated here, that's all it is. The next matrix, okay, is the probability that I go from hazards to response. So these four, 1, 0, 0, 0.5, 0.5, 0, 0, right? 1, 0, 0, 0.5, 0.5, 0, 0, all that. Okay? So that matrix there has all the probabilities that I end up at a certain response given a hazard. So I multiply these two together to leapfrog that layer, and now give me the probability. Sorry, go back one. If I multiply this matrix times this matrix, I get the probability of these damages given that asset. Okay? Or this response is given that asset, and that's what I have. So there's a 99% chance, if on this given day, there's a 99% chance that I have no excitation of that substation. There's a 0.52% chance that I have a 0.05 to 0.1 G excitation. There's a 0.2% chance that I have a 0.1 to 0.2 G excitation, and a 0.29% chance that I have a 0.2 to 0.3 G excitation. Right? That's how we define the response states. And again, then I just need to get the next matrix, multiply that, keep going, and I ultimately end up with this. So here's the probability of loss of that valley load. There's a 99.28% chance that I do not lose the valley load that day. Why is it so high? Because the chances of an earthquake that day are really low. There is a 0.52% chance that I lose half that load that day, and there is a 0.2% chance that I completely lose the load that day. Right? These numbers here are the weighted summation of every probabilistic path through the network. And that was achieved by multiplying those matrices. Multiplying those matrices is solving those integrals. It's integrating over every single probability. Make sense? A little bit? Okay? All right. So now you get to do it. Okay? So what we're going to do is we're going to take, and we'll walk around, we'll help you out. Just have fun with it. It's cool. You should be able to do it in a relatively short amount of time, actually. But what we'll do is we'll say this coast branch. So this transmission line on the coast, okay, we'll take that branch. Our network will look like this. We'll have 3 hazard states, same as before. Nothing bad happens. Cascadia 8, Cascadia 9. We'll have 4 responses, same as before, so that's all the same. But we'll do 2 damage states. For a transmission line, it's kind of like going to be damaged or not. Like it doesn't kind of have half functionality, right? So it's either okay or not okay, and its loss states are either it has full capacity or 0 capacity. Okay, so simplify it a little bit. So those are the loss states that we have. Okay? So what I want you to do is I want you to fill in this chart, 167. There's blanks here to fill these in. So I recommend working in groups of 3 or 4, or if you want to work at the whole table, that's fine. I'll pass a key out. Don't look at the key yet, though. You should wait on that. Okay? And then I'll walk around and try and help people. Okay, so go. Have fun.